All right, let's dive into something that is at the absolute core of every AI model. But honestly, it often gets treated like just another drop-down menu you click on. I'm talking about the loss function. And trust me, it's so much more than a simple setting. It's the entire philosophy that guides how your model learns and sees the world.
And hey, don't just take my word for it. As researcher F. Bernoulli puts it, this one choice is absolutely central. It dictates what your model pays attention to, what it ignores, and really how good it's ever going to get. It's everything.
So why the big deal? What's really going on under the hood when you pick one of these things? Well, it turns out there's this powerful statistical secret that connects your choice of loss function to the very personality of your data, and we're about to uncover it.
So first things first, we got to frame this the right way. This isn't just some technical box-ticking exercise. Choosing a loss function is probably the most foundational, most critical decision you'll make about your model's entire point of view.
So what is it really? At its heart, a loss function is pretty simple. It's the scorekeeper. It's the coach on the sidelines. Every single time your model makes a guess, the loss function compares that guess to the right answer and calculates a penalty, a loss. A huge loss means a big mistake. A tiny loss means, hey, you're getting warm. The entire goal of training an AI is just to make that score as low as possible. That's it. Now, in machine learning, just like in a workshop, you gotta have the right tool for the job. So let's look at the standard everyday pairings, the problems we face, and the loss functions that have become the go-to solutions. You know, most of the time, the problems we're trying to solve with supervised learning fall into one of two big buckets. On one side, you've got regression. That's when you're trying to predict a specific number, like the price of a house. On the other side, you have classification, where you're trying to pick a label from a list, like deciding if an email is spam or not spam. For regression problems, the undisputed king of the hill is mean squared error, or MSE. It looks at the difference between the model's guess and the actual number, and then it squares it. Now that squaring part is the whole secret. It means MSE doesn't just dislike errors, it absolutely hates big errors. Being off by 10 is penalized 100 times more than being off by 1. This makes it super sensitive to those crazy outliers. Now for classification, we bring out a totally different tool, cross-entropy. It works by measuring how surprised the model is by the right answer. Its signature move? It comes down like a ton of bricks on models that are super confident but dead wrong. You know, if your model is shouting, "I'm 99% sure this is a cat," and it's actually a dog, cross-entropy is going to give it a massive penalty. Okay, so this is the playbook, right? This is what every practitioner learns day one. Regression gets MSE. Binary classification gets binary cross-entropy. Multiclass gets its own flavor, categorical cross-entropy. It feels like a set of rules. But have you ever stopped to ask why? Why these specific pairings? Why not something totally different? And this is where it gets really cool. This is the big reveal. These choices aren't just some random convention that everybody agreed on. Nope. They are the direct, logical result of a deep, beautiful, and incredibly powerful statistical principle that connects everything.
And that principle is called maximum likelihood estimation, or MLE. Sounds a little intimidating, but the idea is actually like a three-step detective story. Step one, you make an assumption, a guess, about the underlying pattern of your data. Its statistical personality, if you will. Step two, you use this MLE thing to find the model that is the most likely suspect, the one most likely to have created the data you see. And step three, and this is the magic trick, you find out that minimizing those loss functions we just talked about, it's the exact same thing mathematically as finding that most likely suspect.
So, let's connect the dots. What's the hidden assumption? What are we secretly telling our model about our data every single time we pick mean squared error? We are assuming that the errors our model makes, the little bits it's off by, are perfectly distributed in that classic bell curve shape, a Gaussian distribution. So when you minimize MSE, you're not just reducing error, you're finding the most probable, most likely model if you believe your data's noise looks like a bell curve. Okay, one mystery down. Now what about cross-entropy for classification? What's the hidden story we're telling there? In this case, we're assuming that the outcome for every data point is basically a weighted coin flip, a Bernoulli trial. It's either heads or tails, spam or not spam, cat or not cat. So minimizing cross-entropy is the exact mathematical equivalent of finding the model that best explains the sequence of heads and tails that you actually saw in your data. It's that direct a link. Now, this connection isn't just a coincidence or a couple of neat party tricks. It's all part of a much bigger, more elegant statistical framework that ties all of these ideas together in a really beautiful way. That framework is called Generalized Linear Models, or GLMs, and it's basically the grand unified theory for all of this. GLMs provide the solid statistical bedrock that formally connects the personality of your data, its probability distribution, to the correct loss function, and even to the correct activation function for your neural network.
And check this out. Here's where it all clicks into place. If you start by assuming your data's errors are Gaussian, the GLM framework tells you, okay, then you should use a linear activation and MSE for your loss. If you assume your data is a Bernoulli process, a series of coin flips, the framework points you directly to a sigmoid activation and binary cross-entropy loss. It all connects perfectly. It's one single cohesive story.
So, what's the big takeaway here? What does all this mean for you when you're actually building something? It means your choice of loss function isn't just picking a tool, it's declaring your assumption about the world. Let's just hammer these key points home one last time. Your loss function is a powerful hidden assumption about your data. If you choose MSE, you're assuming bell curve errors. If you choose cross-entropy, you're assuming coin flip-style outcomes. The bridge between these ideas is the principle of maximum likelihood estimation, and the whole thing is wrapped up in the elegant theory of generalized linear models. This should fundamentally change how you approach this problem. The next time you sit down to build a model, don't just ask, what loss function should I use? Instead, look at your data first and ask a better question. What story is my data trying to tell me? Is it a story about bell curves? Is it a story about coin flips? Because that story will tell you exactly which tool to pick.